Hello, wonderful students. How are you doing today? I hope all of you all are doing well, as I am doing well myself. And we are back again to Dr. Saras's classes, and we are back to doing the group theory that we were doing. Isn't it so wonderful? Again am I using that word wonderful? I'm so sorry about that. Please don't be angry with me. I will not annoy you, and I will try and make things even much more simpler. I hope you are enjoying the group theory videos and understanding, even if it is of 10% also if you are understanding, or 50% or 100% also if you are understanding. That's very, very good. Okay, but I hope you all are all understanding the videos of group theory. So I'm back with a new part on group theory, and for this video what we are going to do, the topic is already on the screen. The first one that we are going to talk about are important results on abelian group, some important points, some IMP points, or some examples, okay, on abelian group. Next, normal subgroups, which means we spoke about subgroups, right? Now we have to speak about normal subgroups that are normal. That means, will we get abnormal subgroups? No, you will not get abnormal subgroups, don't worry. You will get normal subgroups. They are normal people, okay? They are normal, very nice, okay? So we're going to talk about normal subgroups in the next second part. And then we will give you some important results or some important points. On normal subgroups. Then we will complete a simple group. What is a simple group? Very simple, right? The name suggests very simple group. Then we will talk about cyclic group, but obviously we will not talk about everything on one video, otherwise you will get mad, okay, and I will get irritated trying to tell you the same thing over and over again. Right, the main point is not to make these videos boring, because group theory actually gets really boring, okay? While students start studying it, they lose interest, they can't understand what's going on, okay? So don't get bored, don't lose your interest. We are going on a very nice journey with this group theory. It's going very, very nice, okay? So let's move on to some important results. The first one, what does it say, students? The first one says a subgroup, oh god, a subgroup of an abelian group is abelian. Simple. So if you have an abelian group, G, and you have a subgroup H of G, then H is also abelian. Not Abetian, sorry, abelian, okay? Please don't write this wrong spelling. Abetian, that sounds nice actually. Anyways, so what does it say? A subgroup of an abelian group is abelian, okay? Let's move on to the second point. First one's over. Second one, it says a finite semigroup which satisfies cross cancellation law is an abelian group. What does that mean? A finite semigroup. A finite means with finite elements. Finite semigroup which satisfies cross cancellation law. Cross cancellation, cancel crossways, right? Cross cancellation law, you remember in small classes, B by A, that is cross cancellation. That's called a cross cancellation, okay? Is an abelian group. Next one, if G is an abelian group and K is a divisor of order of G, then G must contain a subgroup of order of K, that is converse of Lagrange's theorem is true for abelian groups. Okay, now you will get confused with the third one, but nothing to worry. Okay, let me explain this to you. It says if G is an abelian group and K is a divisor of the order of the group. Now you have an order of the group, right? Let's say 10, anything. I am assuming. What happened? Actually, there is a button on the pen, you know, and each time you press the button on the pen, I don't know, something happens, and even if I don't touch the writing pad, as already you people know that I'm doing it on a writing pad. So when I'm writing on the writing pad and if I press the button by mistake, then the haziness comes. You see, I'll show you. Yes, see, haziness comes. I don't know why, but it happens. Anyways, that's not the main thing. Okay, the main thing is what I'm trying to say. So if there is an order of G, let's say 10, all right, and K is a divisor, let's say 5, K is 5. So if you divide, if the order of G is divided, not here, okay, order of G is 10. Okay, now you have to do O of G by K. Okay, when this happens, then what does it say? Then G must contain a subgroup of order K. So G, the group G, has a subgroup of order K. You need to just find that subgroup. What is the criteria for this third point? If there is an abelian group G, understand, listen what I am trying to say. If there is an abelian group G and we can find a number K in that group which is actually a divisor of the order of the group, okay, then in that abelian group G, then in this abelian group G, there is a subgroup, okay, of order K. There is a subgroup of order K. Okay, that is the converse of Lagrange's theorem is true for abelian groups, isn't it? Okay, students. Okay, moving on to, so that is actually the converse of this is actually the this third one is actually the converse of Lagrange's theorem. Okay, let's move on to the fourth one. Every group of order P square is abelian where P is prime. Simple. So if the group has an order of the group is P square. Okay, every group of order P square, then it is abelian. Okay, then it is abelian. You don't even have to give an example and all that. Let's move on to the next one, fifth one. What does it say? If G is an abelian group, then HA is equal to AH such that A belongs to G. This type of things you have to just remember. Okay, this is a law. If G is an abelian group, then HA is equal to AH, right, for all A belonging to G. What is HA? I think this will be the subgroup, okay, of G, and the element will belong to G. Okay, when you multiply that with the subgroup, then you can also get A into H. If you do H into A, you will get the same thing as A into H. Then it becomes an abelian group. Okay, moving on to the next one, sixth one. If every proper subgroup G is abelian, then G may not be abelian. Okay, so if you have a proper subgroup of G, okay, then will you say that the group is abelian? Looking at that subgroup, can you say that the group is abelian? No, you cannot. Okay, you cannot say that just because this subgroup is abelian, its group, its higher part also may be abelian. Not necessarily. Okay, but if the group is abelian, then the subgroup necessarily has to be abelian. Okay, because on the top, the first point, look at the first point. The first point is saying that exactly what I said just now. subgroups of an abelian group is abelian, but the group is not abelian if the subgroup is abelian. Understood? So there are two different things. These two different things, there are two different things. This and this are making a different type of thing. Over here it's saying that if G is abelian, then SG subgroup has to be abelian. But if SG subgroup is abelian, then the group will be abelian. That is not necessary. Okay. Moving on to our seventh point. If G is a finite abelian group, then order of AB divides LCM of order of A for all A comma B belonging to G. So what does that say? If G is a finite abelian group, finite means does not go to infinity, then the order of the element AB, A into B, divides. This will divide the LCM of order of A. So LCM of order of A will be divided by the order of A. Understood? Very, very simple concepts. Very, very simple concepts. Just have to keep that in your head. Okay, this will happen. Some of these points, some of these important points you might want to write. Like this one is important point. Okay, this is the start. It's an important point. Moving on to the next one. Eighth point. In an abelian group. Oh, why am I doing that? Just hold on. Let's see. I'll use a highlighter. Let's see if I can highlight on this. Yeah. In an abelian group, odd order, even in an abelian group of odd order, the product of all the elements of the group is an identity. So can you understand what it is? What does this one is saying? It's so important, you know. I just want to mark this important, like important like that. An abelian group, in an abelian group of odd order, that means the group has an order of the G is equal to odd. Alright, so if order of G is odd, the product of all the elements of the group is an identity element. So if you multiply all the elements, product of all the elements, in the group, GR I'm writing, in the group is an identity. Identity element. Alright, do you understand what I'm trying to say? Okay, so if there is an abelian group of order, then the product of all the elements of the group is an identity element. Very, very simple things, students. Okay, very, very simple things. Learn it simply, understand it simply, keep it in your head. Okay, and definitely we will continue with this video in the further on as we move further. Okay, so that's it for this part of the video, students. We shall continue this in the next part. You keep taking as much help as possible from Dr. Saurabh's classes, because all the help that you will be needing will be provided here at Saurabh's class. Thank you for watching, students.